Welcome to the third lecture of the NPTEL MOOC on parallel algorithms. In the previous lecture, you saw the shared memory model of computation, which is called the parallel random access machine model, in that the processors share a memory and the processors communicate with each other through the memory. But then there are some models of computation in which such a shared memory is not available. We shall see several such models today. These are fixed interconnection network models. So in these models, as I mentioned, there is no shared memory. Each processor is similar to a random access machine, and each processor is connected to some of the other processors. In each step, the processor is capable of sending messages to its neighbors along the connections. We assume that the message is of a word size. And this is again a synchronous machine in the sense that every machine is fed the same clock. So the processors are all executing in lockstep. In each step, each processor performs these substeps. In the first substep, the processor receives input into the local store. Along the connections, its neighbors would be sending messages to it. These messages would be received by the processor in the first substep, and these received messages could be stored in the local store. And then based on the messages received and the previous contents of its local store, it will perform some computations. This is what happens in the second substep. And finally, in the third substep, it generates output that has to be sent to its neighbors along the connections. So that is what a fixed interconnection network looks like. Now we will begin with the simplest of the fixed interconnection networks, which is a linear array In a linear array, we have a number of processors which are interconnected using at most 2 connections per processor. So a processor has a left neighbor and a right neighbor, except possible for the 2 extreme processors. The leftmost processor has no left neighbor and the rightmost processor has no right neighbor. So this is what a linear array. So if you have n processors in a linear array, there are n minus 1 connections. The degree of every vertex, degree is the number of neighbors that a vertex has, degree of a vertex is at most 2. Now, what sort of problems could be solved on such interconnection networks? A wide variety of algorithmic problems could be solved on such interconnection networks. So let us begin with a common problem that we discuss in algorithm courses, which is sorting. Let us say we have to sort n items on a linear array of size n. So let us say we have a linear array of 5 nodes, and on the input line to the first processor we have the input elements coming along. So these are the future input elements 4, 5, 2 and 1 and 3. So before the first step, input element 3 is waiting to enter the first processor. So this is the state of the processor before the first step. So in the first step, only processor 1 is active. The processor 1 had a message waiting for it. So during this step, the message will be delivered to the first processor and that will be stored in the local store of the processor. So now the remaining inputs are 4, 5, 2 and 1 to be coming in the future clock cycles. This machine has no output to generate, and the contents of the other processors are empty. Now, in the second clock cycle, the first processor has 1 coming in. It already has a value stored inside it, which is 3. What it does is this: it compares the incoming value with the already stored value. It finds that 1 is less than 3, therefore, it will send 3 out as a message onto its right neighbor, and the incoming value 1 will be stored instead. The other processors continue to be empty. So, this is what happens after the second step, at the end of the second step. This is the contents of the processors at the end of the first step. Now, in the next step, processors 1 and 2 are active. Let me number the processors from here. So, in the third step, processors 1 and 2 are active. Processor 2 has an incoming message 3 and it has no contents. So, let us assume that processor 2 receives message 3 and stores it in its local memory. The first processor already contains 1 and it has an incoming message 2. So, it compares 2 with 1, finds that 2 is larger than 1, therefore, it does not store 2, but it sends 2 out as a message to the second processor. Its content continues to be the previous one. The remaining input is 4 and 5. So, this is the content of the list at the end of the third step. Now, going on to the fourth step. In the fourth step, the second processor is active. It has a local value of 3 and an incoming message of 2. The incoming message is 2 and that 2 is smaller than 3. So, the second processor will store 2 inside and send 3 along its connection to the third processor as a message. The first processor has 5 coming in and it already has a value of 1. It finds that 1 is smaller than 5, therefore, 5 will be sent on as a message to processor 2. The other processors continue to have empty values. 4 is the next input. So, this is what happens in step 4. So, at the end of the step 4, this is how the list looks like. Now, coming to the fifth step, the third processor has a message 3 coming in and that will be stored there. The second processor has a stored value of 2. It has an incoming message of 5. Since 5 is greater than 2, this processor does not change its contents and sends 5 on to the third processor. Similarly, processor 1 has an incoming message of 4. It finds that 4 is greater than 1, therefore, 4 will be sent along to processor 2. The other processors will contain nothing as before. The list will look like this at the end of the fifth step. So, now you can see that elements 1, 2 and 3 have reached their final destinations. Proceeding in this fashion, in the sixth step, processor 1 has no incoming message. Processor 2 has 4 coming in, but 2 is smaller than 4, therefore, 2 is retained and 4 is sent on to processor 3. Processor 3 has 5 coming in and 5 is larger than 3, therefore, 3 is retained and 5 is sent along to processor 4. So, this is how it looks like at the end of the sixth step. In the 7th step, the third processor has 4 coming in, 3 is what it contains. It will send 4 on to processor 4 and retain its value 3. The fourth processor has 5 and 5 will be stored in its internal memory, and the fifth processor as yet does not contain anything. And then in the 7th step, the fourth processor is active. The fourth processor has 4 coming in and its internal value is 5. Since 4 is smaller than 5, 4 will be stored in its internal memory and 5 will be sent on to the last processor. So this is how the list looks like, the array looks like at the end of the 8th step. Now going on to the 9th step, here all these processors have stabilized. Only the last processor had an incoming message at the end of the previous step. Therefore, in this step, that value will be received and stored in its internal memory. So now the array looks sorted. So the algorithm involved can be summarized like this. This is the first phase of the algorithm where the sorting is done. So in the first phase of the algorithm, each processor does this. It receives an input from the left neighbor. It compares the input with the stored value. Output the larger to the right neighbor. And store the smaller value locally. So this is what the processors do repeatedly. Once again, to take an example, consider the 6th step and look at the third processor. The third processor has a stored value of 3 and there is an incoming value of 4. It compares the incoming value with its stored value. Since the incoming value is larger, the incoming value will be going out as a message to the fourth processor. The smaller of the two values, namely 3, will continue to be stored in its internal memory. Now look at processor 4 in step 7. The incoming value is 4, the stored value is 5. When you compare these two values, you find that the incoming value is the smaller one. Therefore, the incoming value has to be stored in the local memory. So 4 is stored in the local memory. The larger of the two, namely 5, will be sent on as a message to the final processor. So this is the algorithm we have been using in the first phase. So now we claim that if we run the first phase at the end of 2n-1 steps, the array has the input in sorted order. Let us see how we can prove that. First, let us prove the correctness. Looking at this example, we find that when the input streams in through the leftmost processor, it will retain the smallest element. So here the input is coming in the order 3, 1, 2, 5 and 4, and these are the elements that the first processor gets to see. So it initially stores 3, but later on when 1 comes in, it finds that 1 is smaller than 3 and retains 1 and sends 3 on to the next processor. The remaining elements are all larger than 1, therefore they will never be stored in the first processor. Therefore, we find that the leftmost processor looks at every single element but retains the smallest element with it. The leftmost processor retains the smallest element but passes on all the larger elements onto the next processor. Now, if you look at the second processor in this example, we find that the second processor gets to see all the remaining element. That is, it sees the elements 3, 2, 5 and 4 in that order. So, the second processor will first store 3 and then later on when 2 comes in, 3 is replaced by 2. The remaining elements 5 and 4, when they come in that order, will not be stored in processor 2 but passed on to the remaining processors to the right. Therefore, we can conclude that the second leftmost processor retains the smallest of the elements that it gets to see, which happens to be the second smallest element. So, the first processor filters out, the leftmost processor filters out the smallest element and sends the remaining elements onto the second processor. The second processor filters out the second smallest element, keeps it with itself and send the remaining to the third processor. Then naturally the third processor, you can imagine, retains the third smallest element. Continuing like this, we can argue that the ith leftmost element retains the ith smallest element, and in particular the nth leftmost element, which happens to be the rightmost processor, will receive the largest element and then store it with itself. It will never get to see any of the other elements. Therefore, when the algorithm terminates, the ith leftmost processor will contain the ith smallest element and therefore the input will be in sorted order, which proves the correctness of the algorithm, which establishes that the algorithm indeed sorts the input correctly. Now, let us see how long the algorithm runs. At the end of the first step, the leftmost processor has an element. None of the other processors has an element. In the second step, at the end of the second step, the leftmost processor has a message to the right. And then we find that at the end of the third step, the leftmost processor and the second leftmost processors both have an element each. You can see this from this example. At the end of the first step, the leftmost processor has an element. At the end of the second step, the first processor has a message going out to its right neighbor. And then at the end of the third step, the first processor and the second processor both have elements stored in them, but none of the other processors has anything stored in them. So, continuing like this, we find that at the end of the fifth step, the leftmost element, the leftmost processor, the second leftmost processor and the third leftmost processor all have an element each. None of the other processors has an element. And then at the end of the seventh step, the leftmost 4 processors will have elements, none of the others will have an element. So, continuing like this, by induction we can show that at the end of the 2n minus first step, the sequence is sorted. So, this algorithm takes 2n minus 1 steps to get the input sorted, but this is only the first phase of the algorithm when we put the elements in sorted order. In the second phase, we have to get the sorted elements out of the array. So, initially the array was empty, the input streams in and the input is populated into the array, and when the populating of the array is done, the array is in sorted order. This populating of the array will take 2n minus 1 steps. Now, how do we get the values out? The second phase is about getting the values out. Let us assume that we are getting the values out from the leftmost processor. So, we are going to follow the following protocol. Each processor will start passing left when no more input is received from the left neighbor. If there is no more input, then the processor knows that all the input that had to come has come, and now the processor contains the correct value that it should contain. Therefore, this value can now be output from the left end. So, if there is no more input received from the left neighbor, start sending the values to the left. So, let us see when the first processor can start sending the values to the left. The first processor stops getting messages after the 5th step. There were 5 elements coming in this example, and those 5 elements were received in the first 5 steps. Therefore, in the 6th step, it realizes that it has no input message coming in. So, after the 6th step, in the 6th step, since there is no incoming message, it can send one out as a message to the left side. So, the value 1 is now being output, which is the smallest of all the values. So, the smallest of all the values is now being output. Now, the second processor realizes that it has no incoming message in the 7th step. Therefore, in the 7th step, the second processor will send out value 2 to its left neighbor. This is the output that is generated by the second processor. So, when the first processor receives this value from the right in the 8th step, it will pass it on to the pass it out along the left connection. So, in the 8th step, this will be passed on as an output onto the left side of the first processor. So, let us assume that this is where we receive the output. So, the first output will be received in the 6th step and the second output will be received in the 8th step. Now, look at processor 3. Processor 3 does not receive any message in the 7th step. Therefore, in the 8th step, processor 3 will start sending out its value to the left. So, now you can see the pattern. In the 6th step, the first processor sends out its value. In the 7th step, the second processor sends out its value, and in the 3rd step, in the 8th step, the third processor sends out its value, all to the left side. The output received at the leftmost end of the array would be first in the 6th step and then in the 8th step and so on. In the 9th step, processor 4 will be sending out its content to the left side, and processor 2 will be sending out its content to the message it had received to the left side, which is the value 3. So, these two messages will still remain in the system at the end of the 9th step, and this continues. Therefore, in general, what we can argue is this about the second phase: by the nth step, all the input is received. So, the first processor can start sending out messages from the next step. So, the first output, which is the smallest of all the elements, this happens in the n plus first step. The second output happens in the n plus third step. You can see that the outputs are all spaced by one step, that is, between two consecutive outputs there are two steps. The first output happens in the 6th step, whereas the second output happens in the 8th step. So, continuing like this, the third output happens in the n plus 5th step and so on. Therefore, the nth output, which is the last of the outputs, happens in step number n plus 2n minus 1, which is 3n minus 1. So, by the 3n minus first step, you have received all the outputs. So, here you should see that the elements will get sorted only by the 2n minus first step, but many outputs would already be received by that step. The output will start coming out from the n plus first step. Therefore, the time complexity of the algorithm is 3n minus 1. The algorithm uses n processors, a linear array of n processors, and runs in 3n minus 1 steps. So, this is the first algorithm on an interconnection model that we have seen. On a linear array, on a streaming in input can be sorted in 3n minus 1 steps when the size of the array is n. Now, in every situation, this may not be what we want. Here we considered an input that was streaming in. Suppose the input was already stored in an array. In that case, how would you sort the array? For example, let us say we have a linear array that contains these elements. In this order. So, let us say these are the contents of the consecutive processors of a linear array. To sort them using the previous algorithm, we would have to output these elements and then input them back into the array and sort them as we did before. So, to get them out of the array, we will have to spend n steps, and then the 3n minus 1 steps algorithm will have to be executed for a total of 4n minus 1 steps. But as it happens, there exists an algorithm which is much faster. This algorithm is called the odd even transposition sort. So, in the odd even transposition sort, we group the elements into groups of size 2 each and then sort each group. In the next step, the grouping is different. So, let me demonstrate. In the first step, I will group the elements in this fashion. The first 2 elements will form a group, the next 2 elements will form a group, the next 2 elements will form a group, and so on. And then each group is sorted by comparing and exchanging. So, within the first group I have 2 and 5, we compare 2 with 5, we find that 2 is smaller than 5, so there is nothing to do. So, the first 2 elements will be retained as it is. When we look at the next pair of elements, which is 8 and 1, we find that 8 is larger than 1. So, when we sort them, 1 should come first. Therefore, we compare them and then exchange them. After the exchange, 1 will come to the left side and 8 will come to the right side. Mind you, all these elements are on linear array Therefore, there is a connection between adjacent elements. So, such a swap is possible by sending the elements as a message between two adjacent processes. When we compare the next pair of elements, we find that they also should be exchanged to be in sorted order. The last pair is already in sorted order, so there is nothing to do. So, in the first step, what we have done is to pair of the elements from the left end. Within each pair, we compare the elements and exchange them if necessary. This exchange happens along the interconnection in the linear array. Now, in the next step, we will group the elements in this fashion. We leave out the first element and then we form groups of 2 each. And then again, within each group, we will compare and sort. Mind you, all the groups are being sorted in parallel. So, this is only the second parallel step, whereas this was the first parallel step. So, when we compare and exchange, 2 is not being compared with any element. So, 2 retains its original position. 5 and 1 get swapped, 1 will come to the left and 5 will come to the right. 4 and 8 also get swapped, 3 and 6 also get swapped, 7 is not being compared with any element. So, this is the content of the linear array after the second step. So, this is how it looks like at the end of the third step, at the beginning of the third step. In the third step, we again go back to the original odd even pairing. So, in the first step we had an odd even pairing, an odd element is compared with the next even element, whereas in the second step we have an even odd pairing, an even element is paired with the next odd element. In the third step we again have an odd even pairing. So, 2 is paired with 1, 5 is paired with 4, 8 is paired with 3 and 6 is paired with 7. And we perform a comparison and exchange within each group. So, the first group is set right, the second group is set right, the third group is also set right, the fourth group is already in sorted order. So, the content of the array will look like this at the beginning of the fourth step. The fourth step is again an even odd pairing step. Every even element is paired with the next odd element. So, 2 is paired with 4, 5 is paired with 3, 8 is paired with 6. And then we perform a compare and exchange. 1 is without a pair, therefore 1 remains as it is. 2 and 4 are already in sorted order. 5 and 3 are set right to 3 and 5. 8 and 6 are set right to 6 and 8. 7 is a loner. So, this is how the array looks like at the beginning of the fifth step. Now, again we have an odd even pairing. 1 and 2 are paired, 4 and 3 are paired, 5 and 6 are paired, 8 and 7 are paired. When we compare and exchange in the fifth step, we will have 1, 2, 3, 4, 5, 6 and 7, 8. So, the elements are now in sorted order. So, without having to take out all the elements and then stream them back in and use the first algorithm, we have managed to sort the set of elements in place. The elements have always been within the linear array, and in every single step we compare adjacent elements and exchange them if necessary. This algorithm is called the odd even transposition sort. The odd even transposition sort algorithm as I explained proceeds like this. In the first step we pair odd elements with the next odd elements with the next even elements. In the second step we pair even elements with the subsequent odd elements and so on. And then within each pair we perform a comparison and exchange if necessary, so that the elements will be in sorted order. If we continue this process, finally the elements will be sorted. We shall see the correctness and the analysis of the algorithm later, but at the moment I will tell you that this algorithm terminates in n steps, which is far better than the 4n minus 1 we proposed earlier. That is, if you stream out all the elements and use the first algorithm we saw, which runs in 3n minus 1 steps, the total number of steps is 4n minus 1. So, this is far better than that. So, we have seen a couple of algorithms on the linear array now. Now, let us move on to an interconnection network that is slightly more complicated. In this case, the processors are arranged in a two-dimensional array. And the processors are interconnected using horizontal edges as well as vertical edges. So, here you find that there are three kinds of nodes. There are the interior nodes. These are the interior nodes. The interior nodes have 4 edges, 2 horizontal edges going out of it and 2 vertical edges going out of it. So, interior edges have a degree of 4. Then there are the corner edges. The corner edges have 1 horizontal edge and 1 vertical edge going out of it. So, the corner edges have a degree of 2 each. Any node which is neither an interior edge nor a corner edge is a boundary edge of this sort. These edges have a degree of 3. So, we can say that the maximum vertex degree of a node in a two-dimensional mesh is 4. The boundary edges can have a degree of 2 or 3. The corner edges in particular have a degree of 2, and the boundary edges that are not in the corner will have a degree of 3. Now, once again let us see how we sort on a two-dimensional array. Let us say we have the elements distributed on a two-dimensional array in this fashion. Here B is the hexadecimal B. Let us say we have a two-dimensional array, two-dimensional mesh in which the elements are stored in this fashion, and these elements have to be sorted. So, here A, B, C, D, E, F are the hexadecimal values 10, 11, 12, 13, 14 and 15. So, to sort them, what we do is this. In the first step of the algorithm, we sort the rows horizontally. The odd rows are sorted from left to right and the even rows are sorted from right to left. The odd rows are sorted from left to right. Therefore, the first row will be sorted into 2, 4, 7 and B. And the second row is sorted from right to left. Therefore, the second row will be from right to left 0, 9, A and E. And the third row again is sorted from left to right. So, we have 1, 3, 6 and D. And the fourth row is sorted from right to left. We have 5, 8, C and F. So, this is what happens in the first step. In the first step, every row is sorted. The odd rows are sorted from left to right and the even rows are sorted from right to left. For sorting the rows, we use the odd even transposition sort, which we have just seen. So, if we have an n by n mesh, then a row has a size of n and a column has a size of n. Therefore, the row can be sorted in n steps using the odd even transposition sort. So, this step can be executed in n parallel steps. Now, in the second phase in the second step of the algorithm, we will sort every single column of the linear array. The columns are all uniformly sorted from top to bottom. So, when you sort the columns from top to bottom, the array that we get is this 1, 2, EF is how the first column looks like. The second column is 3, 4, A and C. And the third column is 6, 7, 8 and 9. And the fourth column is 0, 5, B and D. So, here every column is sorted from top to bottom using odd even transposition sort. Therefore, the time taken is the size of the array, which is n, if we consider an n by n mesh. Now, in the third phase of the algorithm, which is similar to the first phase, we sort the rows, but we change the direction of the alternate rows. The first row is sorted from left to right. Therefore, the first row will contain 0, 1, 3 and 6. The second row is sorted from right to left. The second row will contain 2, 4, 5 and 7. The third row is sorted from left to right again. So, the third row will contain 8, A, B and E. The fourth row is sorted from right to left. So, it will contain 9, C, D and F. So, after the first 4 phases, the array will look like this. Now, in the next phase, we once again sort the elements top to bottom. This is the initial array. This is the array after the first step. This is the mesh after the second step. And this is the mesh after the third step. Now, in the fourth step, we will sort the columns vertically. The first column therefore will be 0, 7, 8 and F. The second column will be 1, 5, A and D. The third column will be 3, 4, B and C, and the fourth column will be 2, 6, 9 and E. Do they look sorted now? They do, except in that the alternate rows are in reverse order. That is, the first row is sorted like this, the second row is sorted like this, the third row is sorted from left to right, and the fourth row is sorted from right to left. So, combining them, we find that the elements are in sorted order. So, we can say the elements are sorted in a snake-like order. And you can see that the elements get sorted surprisingly fast. In fact, we can show that on a root n by root n mesh, the elements can be sorted in order of root n log n steps. The analysis as well as the correctness proof we shall see later. Two-dimensional meshes can be further generalized into three-dimensional meshes. In a 3D mesh, a processor has neighbors to the left, to the right, above, below, and also in the front and to the back. So, an interior processor in a three-dimensional mesh has a degree of 3, degree of 6, 2 in each dimension. Of course, the boundary processors will have fewer degrees. In particular, a corner processor will have only one neighbor along each dimension. So, the corner processors will have a degree of 3 each. And then we can consider 4-dimensional meshes, 5-dimensional meshes and so on, increasing the connectivity of the meshes. When we have a 2-dimensional mesh of processors, instead of connecting them using horizontal and vertical edges, we could connect them using binary trees that hold auxiliary processors. For example, you could construct a binary tree over the first row of the mesh of processors in this fashion. Similarly, over the second row we construct a binary tree. And so on. Similarly, we could construct processors, we could use auxiliary processors to construct binary trees over the columns as well. We could construct a binary tree over the first column in this fashion. Similarly, we construct a binary tree of every single column. So what we get is a two-dimensional mesh of trees. We shall also see several interconnection networks that are closely related to hypercubes. I will define what a hypercube is in this lecture, and during the course of the program we shall see several interconnection networks that are related to hypercubes. A hypercube of dimension 0 is a single processor without any connection. A hypercube of dimension 1 is constructed by taking two copies of H0 and connecting the nodes. And then to construct a hypercube of dimension 2, we take two copies of H1 and connect the corresponding nodes. We can name the nodes of a hypercube using binary strings. So let us say the nodes of H1 are named in this fashion. The left node is named 0 and the right node is named 1. To construct H2, we took two copies of H1. So in them the left node is named 0 and the right node is labeled 1. But to distinguish the two copies, we will add one extra bit. So let us say the top copy is labeled 0 and the bottom copy is labeled 1. So a hypercube of dimension 2 can be labeled in this fashion. Then a hypercube of dimension 3 can be obtained by taking two copies of two-dimensional hypercubes. So this is one copy. This is another copy, and then we connect the corresponding nodes. Nodes that occupy the same relative positions are connected. So these nodes are named in this fashion: 0, 0 and 0, 1 along the top edge, and 1, 0 and 1, 1 along the bottom edge, and here also the same. So you can see that nodes of the same name are connected between the two copies. Now to distinguish the two copies, we will add one extra bit. The four nodes of the outer cube are given a label of 0 and the four nodes of the inner cube are given a label of 1. So this is a hypercube of dimension 3. Now coming on to the fourth dimension, we take two hypercubes of dimension 3 and interconnect the corresponding nodes. So, this node corresponds to this. These two are corresponding nodes, they are connected, and these two are corresponding nodes and they are connected. These two are corresponding nodes and they are connected, and so on. So, this is how you construct a hypercube of dimension 4. So, you can see that as you go from one dimension to the next, the number of nodes in the hypercube doubles. In H0, there is only one node, 2 power 0 equal to 1. In H1, there are two nodes, 2 power 1 equal to 2. In H2, there are 4 nodes, 2 power 2 equal to 4. In H3, there are 8 nodes, 2 power 3 equal to 8. And in H4, there are 16 nodes, 2 power 4 equal to 16. And the vertex degree is equal to the dimension of the cube. For example, in H4, a node has a degree of 4. For example, this corner node has 4 adjacent edges. Every vertex has exactly the same vertex degree here. So, in general, if you take an n node hypercube, this has a dimension of log n. When you have a hypercube of n nodes, then n would have to be a power of 2, and therefore log n is an integer. Log n to the base 2 is an integer. So, we consider an n node hypercube. In this, the degree of every node is log n, which is equal to the dimension. So, in general, in Hk, a hypercube of dimension k, the degree of every single node is k. There are several interconnection networks that are closely related to hypercubes, namely the butterfly networks, the cube connected cycles, the Bruin graphs, shuffle exchange graphs, and many others. We shall see some of them during this course, and we shall design algorithms on them and analyze the algorithms. That is it from the third lecture. Hope to see you in the next lecture. Thank you.